Welcome, everyone. Thank you for joining today's webinar. My name is Ashley Bianco, and I'm the Marketing Supervisor at Strem Chemicals. I will be your host today. Today's webinar topic is exploring the impact of ligand and catalyst selection on petrochemical applications. Strem is happy to be hosting today's webinar and to have two technical presenters from Solvay here to talk about their technology. Our presenters are Dino Amoroso, Solvay's North American Account Manager, and Eamon Conrad, Solvay's Global Business Development Manager. Before we get started, I would like to mention a few points. First, if you would like to ask a question, please type it into the question box in your control panel. You can do this throughout the meeting, and I will bring up the questions during our Q&A session at the end. Also, we've added some useful handouts in the control panel for you to reference. Please take a look and download them to learn more about the products related to today's webinar. Lastly, this session is being recorded and will be available to all registrants after the meeting. To start, here's an overview of our presentation. First, we'll discuss Strem, Solvay, and our partnership. Second, we will touch on chemistry for manufacture of phosphine ligands, followed by applications in petrochemicals, then developing unique solutions, and we will close out with a summary and questions. Next slide, please. Thank you. Now I'll give everybody an overview of Strem. For those of you who don't know our company, we were established in 1964. We have been a brand name for over 55 years now, and we have gained significant experience in manufacturing and handling high quality inorganics and organometallics. We currently offer over 5,000 specialty chemicals in our catalog. Those kind of products include lab chemicals, cGMP products, high pressure materials, custom synthesis as well. We serve a variety of customers, including academia, industry, and government R&D labs. In addition to R&D, we also deal with commercial scale business in many industries, including pharma, microelectronics, chemical, and petrochemical. Strem's experience in handling, focus on quality, and reach in the market were driving factors in beginning our partnership with Solvay. Our collaboration allows Strem to handle multi-kilo sample distribution while Solvay manages the industrial scale. Solvay is a global leader in phosphorus chemistry, which fits perfect with our product line, and we're happy to be working together. With that said, I will now hand it off to Dino to talk about Solvay and begin the technical presentation. Dino, you're up.
Thank you, Ashley. It's a great pleasure of ours to be able to certainly work with Strem and also have the opportunity to present a little bit about the chemistry and applications of phosphorus in catalysis. And as far as our partnership with Strem, it certainly allows us to expand our reach and bring our capabilities to a broader audience. And among those capabilities in phosphorus chemistry is a differentiated product and technology offering. So we have a wide range of phosphorus chemistry and technologies. We'll highlight some of those today with some specific focus in the area of catalysis. Solvay's very long history in phosphorus chemistry, over 160 years, means that we've been certainly involved from a very early point in time, but also have extensive experience in innovating over those years. One thing that's unique to Solvay in the realm of phosphorus chemistry is our ability to shepherd chemistries and technologies from research to pilot all the way to large-scale manufacturing. With all of this, we do this in partnership with our customers. We listen, we learn to understand their needs, translate them into something concrete from the point of view of a solution that relies on phosphorus chemistry. And we support all of this with a secure and consistent supply. So we focus on quality controls and timely order fulfillment, leveraging our global footprint to make sure that Solvay is the right partner for commercialization of phosphorus technologies. Of course, the chemical industry is increasingly being challenged to reinvent its sustainability agenda. Solvay is certainly a part of this, participating with our Solvay One Planet goals. Solvay One Planet is an integral part of our strategy. Sustainability is at the heart of our operations, and we're setting the bar higher across the entire value chain with our new goals that extend our focus on our impact on climate, resources, and a better life for our employees and communities. Everything we do takes into consideration the Solvay One Planet goals, and we leverage that to improve the way we measure the impact of our solutions. So phosphorus chemistry has many applications, and so what that means is we serve a range of markets, and we'll highlight specifically catalysis today, but the materials that Solvay provides in the phosphorus sphere span applications from things like agriculture, where we have cylinderized phosphine gas as a fumigant, materials that find their way into textiles as flame retardants, phosphorus products that are used in applications like oligonucleotide synthesis and genome sequencing. In electronics, we have high purity phosphine gas, as well as high purity derivatives that are used in the manufacture of quantum dots. Phosphonium salts that find their way into biocidal applications, products that find their way into things like extractions, and in particular catalysis, which we'll focus on shortly. Phosphonium salts and other additives that are used in plastics and epoxy applications, and then a host of other materials and applications that things like metal extraction and recycling, where any number of phosphorus products have been used commercially to expand those markets. Of course, with all of these markets, the goal for today is to really talk about catalysis. And so as far as Solvay's phosphorus technology goes in catalysis, you'll see shortly that it really begins with elemental phosphorus, P4. From there, we get into things like precursors to ligands, ligands themselves, and of course, homogeneous catalysts as well. And these materials find application in a range of catalytic applications, whether it's hydroformylation and coupling chemistries that are used in things like drug synthesis, olefin metathesis hydrogenation, ethylene dimerization. We're going to show you a range of applications and products today to really emphasize that Solvay really is a leader in supplying phosphorus-based ligands at an industrial scale. So before we get into the catalysis applications, we want to talk briefly about the chemistry that we leverage in the manufacture of essentially phosphine ligands and some of the phosphorus derivatives that aren't necessarily ligands, but are also relevant to the field of catalysis. And so where it all begins for Solvay is with elemental phosphorus, or P4. So at the center top of the screen, you see P4, essentially the central piece. For the discussion today, we'll focus primarily on the left side of the screen, the left branch. So from P4, Solvay derives phosphine gas. So Solvay is unique in its ability to handle high pressure phosphine gas at scales that are unparalleled in the industry. From phosphine gas, if we follow the arrows, we can access from the left on the bottom, primary, secondary, and tertiary alkyl phosphines. Of course, derivatives of those include things like phosphonic and phosphinic acids, oxides, sulfides, etc., phosphonium salts as well. And we'll see examples of not just alkyl phosphines as ligands in catalysis, but even some phosphonium salts and oxides that play a role in catalysis. And so the key piece here is how do we get from P4 to alkyl phosphine derivatives? And so what that comes down to is how do we make phosphorus carbon bonds? And one of the sort of foundational chemistries that we practice is the free radical addition of phosphine to olefin. So many of the alkyl phosphine derivatives that you'll see today will have been derived through radical addition. The scheme I'm showing on the screen now is a simple sort of radical initiated mechanism. So any sort of radical initiator will react with phosphine to generate a phosphine-based radical. That phosphine radical can react with an alpha olefin to generate the intermediate radical, the carbon-centered radical that you see on the right side of the second reaction. Of course, that carbon radical will react with free phosphine regenerating the phosphine radical and leaving behind a primary alkyl phosphine. So this is a fairly simple radical mechanism. I think most people who studied chemistry have seen things like this. The nice thing here is that we have a lot of parameters that we can leverage to tune the chemistry or the products. Things like time, pressure, concentration, and nature of the radical initiator all allow us to tailor the products that are being derived. So this scheme shows us primary alkyl phosphine as the product. Certainly, as you cycle through this mechanism, you can install a second and third alkyl phosphine, leading to secondary and tertiary alkyl phosphines as well. So here's an example of a product derived through the radical initiated mechanism. So this is derived from the reaction of phosphine with butene. So this leads to, in this case, triene-butylphosphine, which is also known as our Cytop 340. The chemistry is quite simple in terms of that mechanism that we showed earlier. Generally speaking, high 90% yields of the trialkyl phosphine derivative. The main, let's say, impurity is actually an isomer, which is shown on the top right of the diagram with the secondary attachment to phosphorus. So still retaining essentially the same structural formula. Some other impurities include what we call telomers or oligomers, where you have elongation of the alkyl fragment due to the radical propagating with another olefin. And then some elimination products as well that give rise to some unsaturation in the products. And so this is just one example. You can imagine as we look at the variety of olefins that are available to us, it really speaks to the sort of limitless access to diverse structures that exist through the radical chemistry. And of course, the product distribution that we obtain through that chemistry is dependent on the nature of the olefins. On the far left, I've got a few simple alpha olefins. These react very readily, very predictably under radical conditions to give you things like primary, secondary, tertiary alkyl phosphines. Cyclic olefins are similar in nature, so monounsaturated cyclic olefin will add just like an alpha olefin to phosphine. Cyclooctadiene gives an interesting structure, which Eamon will talk about shortly as we get going into some of the products. Functionalized olefins are also accessible to us to generate derivatized alkyl phosphines. Things like alcohol and nitrile functionalized alkyl phosphines are certainly accessible. And then on the far right, aromatic olefins are a little bit more challenging. So you might imagine aromatic olefins have a tendency to polymerize under radical conditions. And so those are generally less useful under radical conditions, but certainly the other categories are quite useful and allow us to access a range of alkyl phosphine derivatives. Radical chemistry isn't the only chemistry we use to install phosphorus carbon bonds. We also use acid catalyzed addition of phosphine to olefins. So under strongly acidic conditions, an olefin like isobutene will generate a carbocation at the tertiary carbon. Phosphine will react, generating ultimately a tertiary butyl substituent on the phosphine. So under these conditions, you can install two tertiary butyl phosphine alkyl fragments on the phosphine. If you were to compare this to the radical mechanism, you would install the isobutyl fragment. So I've shown those two in comparison in the middle of the screen there. Interesting to note here that under acid catalyzed conditions, only two isobutylene fragments will add to phosphine, giving rise to ditertiary butyl phosphine, which is known as our Cytop 242. Under radical conditions, the favored product is the tertiary alkyl phosphine, which is triisobutylphosphine, known as Cytop 341. Beyond acid catalyzed addition, we have some other techniques that we use to make phosphorus carbon bonds. A little bit more unique here is the Michael addition of phosphine to activated olefins to show. So in that top scheme, you see the cyclic structure. Another interesting one is the addition of phosphine to 2,4-pentane dione, which gives rise to the phosphoadamantane structure on the bottom scheme. That's also known as our Cytop 216, and you'll see an example of that shortly as Eamon gets into the catalysis applications. And so from here, Basically, I'll turn it over to Eamon to start to discuss some of the applications of the molecules or fragments of catalysts that we've talked about already. Eamon?
Thanks, Dino, and thanks everyone for joining today. Like Dino said, in this section here, we're going to focus a lot on some of the applications and the uses of phosphines in homogeneous catalysis in particular, and then some of the advantages and differences that you can develop in your chemistry as a result of using phosphorus products. Next slide. So, I mean, ultimately, catalysis is anything that can facilitate the conversion of one molecule to another. And they're essential to not just petrochemical industry, but a variety of industries, right? Whether you're looking at pharmaceuticals, specialty chemicals, polymers, what have you. And they're really a great opportunity to innovate and provide some, to be a key enabler in sustainable processes. Catalysis offers a variety of benefits, the ability to reduce CO2 emissions, reduce chemical use, reduce energy input, less waste and higher yields of desired products, but also different products, right? Depending on what the needs of your customers or your applications are. Catalysis is really important to petrochemicals. As we'll talk about, it does a lot of the basic building blocks in chemistry, but it also allows the conversion of these chemicals as well to other more value-added and specialty products as well. The industry itself is quite large. It's around $33 billion a year and growing. And about a quarter of this is in the homogeneous space. And so that's what we're going to talk about today, is really some examples of where homogeneous catalysis with phosphine ligands in particular can give you some advantages when you think about selectivity, activity, lifetime or product distribution at the industrial scale. Next slide. So first of all, the interest in phosphorus catalysis is really driven by a few things. And one of them is the item that Dino mentioned, is the tunability. We're going to talk about the diversity of the structures and how this applies and changes and alters the chemistry and the products that are coming out. The products themselves, they're very thermally stable. They have a lot of chemical stability with them and a lot of variety in reactivity and selectivity. Ultimately, they provide that key balance with the metal to provide critical process efficacy with a variety of different metal species. From a practical standpoint, the products are available in multiple forms. The ones that we'll talk about, some of them are liquids, some of them are solids. We offer them in process solvents as well. And critical to this is we offer a lot of support with product stewardship, particularly around the safety and handling of these products. And we have established manufacturing routes to what we call the right scale. So the reality is with catalysis is some applications need 100 kgs, some need 100 tons, and there's a whole wide range of volumes in between there, right? And we support applications across that bandwidth. And as I mentioned, we're really a strong player in safety on this too. We're a leader in safe supply of these, and that's one of our hallmarks and our credentials. Next slide. So first I want to talk about, a bit more about modularity and diversity within these systems. One of the areas that we produce products in is secondary phosphines. And on the bottom of the screen here, we see we have a variety of different systems. Some are bulky, like tertiary butyl, some less bulky, like isobutyl. And these serve as building blocks really to a variety of different ligands. And if you think about a very simple example, such as Josephos, changing that one position changes a lot of the efficacy of the chemistry. And, we supply into research labs these types of building blocks, but we also do conversion of these up into more complex and elegant molecules. So something like diphenylphosphine will convert to what we call Rhodophos CP100R. This is chirophos, a lot of people know it as, which is actually used as a chiral hydrogenation ligand in petrochemical, and we'll talk a bit more about that later on. Next slide. The modularity of these systems is really important in the petrochemical field. If we take one example that we have, the Cytop 282 that Dino mentioned earlier, this is a product we make from the reaction of cyclooctadiene and phosphine gas, and you get a mixture of two bulky alkyl phosphines. These can be separated by selective protonation, But what they really are is a precursor ligand that offers a lot of bulk as an alternative to, say, something like tertiary butyl or adamantyl, which is much more expensive. That pH bond can be modified. You can put something like an alkyl group on it and develop a metathesis ligand. You can put some different amine functionality on it for dehydration ligands. And also, in this example on the bottom, is a phosphine oxide addition to the end of it, and this is used as a hydroformylation ligand. So having these at commercial scale to build up these other potentially relevant commercially scale applications is critically important, and that's really an area we focus on. Next slide. So the first application I really want to dive into is about ethylene conversion. Ethylene is one of the most important building blocks in the chemical industry, and it's used to be converted into a lot of higher value products. But when you want to convert ethylene, it's really control of that conversion that's critical. If you're looking at, say, dimerization to make C4s, trimerizations or tetramerizations to make C6 or C8, or longer oligomers and polymers of these, you really need to have that tight control for the product distribution to get what you want in your application. You know, in the simplest form, if you look at the conversion of ethylene to C4, you know, even just from this one step, you have two potential options, right? You can have 2-butene form or 1-butene form. And, you know, depending on what you want to do, say make propene, octene, or alkylate chemistry, you may want 2-butene. But if you're looking at, say, polyester copolymers or things like butylene oxide synthesis, the 1-butene is the desired product. Next slide. So our focus is really on the formation of 2-butene. This is a key raw material for two processes. One's the production of alkylate for gasoline, and the other is the formation of propylene. And in both of these processes, you know, to get to your 2-butene, you know, you want to have maximum production of that product because that will allow you to have a higher quality output and higher conversion. And so that olefin dimerization requires a catalyst. Next slide. The product that we offer in this space is a nickel-based catalyst, so it's on the bottom of the screen here, the nickel dichloride bis tributylphosphine, we call Rotafos NiCat. And this is one that's employed industrially as that dimerization catalyst. So in the presence of a Lewis acid like ethyl dichloroaluminum, you get basically selective formation of 2-butylene. So you get that isomer and you get very good conversion to that dimer. This nickel catalyst is also effective in the dimerization of things like propylene. Noticeably, what you'll see here is it favors the formation of internal olefins as opposed to alpha olefins. But it can also be used as well in different processes for polymer formation and then cycloaddition chemistry as well. Next slide. If you want to make something a little bit longer from ethylene, say you want to make hexene or octene, again, control is critically important. Having things shorter or longer can make for more expensive purification processes, less yield of desired products or impurities that you want to get rid of. Hexene and octene are both used in different polyester grades, but they also have some unique uses of, say, making different aldehydes or plasticizers for octene, or things like heptanal from hexene. Next slide. This chemistry of the ethylene to octene is really dominated, I think, in a homogeneous way from chromium catalysis. There's some very effective processes out there in the literature that use chromium with this phosphine ligand shown here that we call Rotafos PNP12. It's ultimately used for the selective formation of things like 1-octene. You can also produce hexene as a second major project in this system. But of note as well, the ligand itself is modular and can be modified to be tuned to other different process conditions. So the phosphine itself can be altered with the alkyl or aryl substituents on it. But you can also modify the nitrogen backbone as well. Next slide, please. You know, we'd be remiss to talk about ethylene conversion and not talk about the Shell higher olefin process, which is really one of the most long-standing examples of homogeneous catalysis in industry. You know, Shell has done this process since the 70s, And, it's looking at the conversion of ethylene to oligomers, so C10, C12, C14, to these even-numbered linear alpha olefins. So in these cases, looking at the olefin at the terminal position. And then these products are subsequently isomerized and hydroformylated into alcohols. These types of ligands are really interesting, and we like to talk about because they show a nice example of how you can make relevant industrial solutions from relatively simple starting materials that are supplied by Solvay or sampled by Strem. You can take a secondary phosphine, convert it to the lithium phosphide species. Subsequent elimination of lithium chloride, you can attach a phosphine to the aryl backbone here, and then a simple protonation leads you to a desired ligand here. And this is really nice because this process has been established and provided really efficient industrial solutions for quite some time. Next slide. To continue the discussion around ethylene, sometimes the polymerization of ethylene is the end goal. And like with any polymerization reaction, control of polymer chain length is important, right? And also the distribution of the molecular weight of those polymers that you make, because ultimately that will affect the properties of your polymer system and how well it performs or doesn't perform in a specific application. There's a family of catalysts called single site catalysts, and here are just two examples of them that use phosphinamide ligands on them. So that's the PN double bond here. And these are really nice catalysts because they're very effective at controlling molecular weight and size distribution. The balance between the titanium and the phosphorus in these systems is really critical to these processes. And the alteration of the phosphine on this can also alter the end properties that you end up with and the type of system you get. However, there's examples in the literature, such as this example using triacylbutylphosphine as the ligand on the titanosine catalyst, that you can get really tight control over molecular weight and distribution. The catalysts themselves are relatively stable and easy to handle. And as I mentioned, they're also easily modified, which is a nice feature for further development of the chemistry. Next slide. Telomerization is an interesting reaction in the petrochemicals because ultimately you're converting butadiene into a higher value product for specialty chemicals. It's a very atom economical process. It's tolerant to nucleophiles, but in a lot of cases, the homogeneous chemistry really requires a phosphine ligand. A lot of current systems use triphenylphosphine. Although it's cheap, it's relatively susceptible to oxidation and also has low selectivity in a process. This work here showed how you could take a palladium catalyzed reaction with what we call the Cytop 292 ligand. So this is a derivative of the Cytop 216 ligand that Dino mentioned earlier. And when this ligand is employed in this reaction, you get significant benefits that really end up providing, relevant benefits at an industrial scale. The conversion when you switch from triphenylphosphine to something like Cytop 292 is significantly better. Selectivity for the isomer forming is better, and also the overall yield is about 10% better in this case. And all these combined really add to significant cost improvements at the industrial scale. Next slide. There's other ways to produce olefin species. One of those is metathesis. Metathesis exists predominantly in petrochemical as a heterogeneous process, but there's been a lot of work done over the years to develop some really attractive ruthenium-based catalysts. And so this is just one example on the side here where you have a ruthenium catalyst. You've got a carbene ligand and a phosphine ligand, and that pairing together really provides a very useful reactivity in the system. These catalysts are really nice as well too because they're robust to air, water, and oxygenates, and they provide high reaction rates and selectivity. If you look at the self-metathesis of something like 1-octene and using tricyclohexylphosphine as the phosphine ligand on here, you can get, in the right conditions, very high, around 600,000 turnover number with very high selectivity of the desired product as well. And when you compare this to triphenylphosphine, which is also employed in these, it's more than double the reactivity levels in these situations. And so this is a nice example of homogeneous catalysis providing a nice solution to this type of synthetic challenges. Next slide. So the next reaction and application I'm going to talk about is hydroformylation. So the hydroformylation is one of the highest volume homogeneous catalyzed reactions in the world. And, it's ultimately, the conversion of an alkene to an aldehyde. This example here shows that, with your catalyst system, ultimately you can have the carbon, the CO adding at 2 different positions within the system. Depending on your application, you want one or the other, or sometimes both. Phosphine modified versions of this chemistry was initially discovered in the 60s and has been part of our lives since then. It's really dominated in the homogeneous sense by rhodium and cobalt. And as we'll show on the next few slides, many of these really require the phosphorus ligand, and there's still some really exciting discoveries being made in this field. Next slide. I'm going to start with the hydroformylation of propylene. So this is a rhodium-based process. You can do it in the chart as you see in the first row here in the absence of a phosphine ligand. However, the addition of something like tricyclohexylphosphine or Cytop 366 in a relatively small ratio, so just 3 to 1, almost doubles the activity of this catalytic process. So you see the same distribution of products, which is good if that's the distribution, say, that you're looking at, and you don't want to modify that, but you get that increased activity. So this is a really good example that shows the addition of a phosphine to a homogeneous catalyzed reaction that is not using a phosphine can actually provide benefits on throughput, ultimately at the end of the day. The bottom 2 lines in the table also highlight why it's important to screen and understand your catalytic system as much as possible, because the simple premise of adding a phosphine is not always necessarily the right solution. If you look at something like trioctylphosphine, you actually decrease the reactivity in this case. So you need to find that right balance of something that can help the chemistry, but not ultimately stop the chemistry. And in these cases, ultimately what the determination was, sterically hindered phosphines enhance the reactivity of a reaction like this, where non-hindered ones do not. Next slide. I wanted to talk about this example of hydroformylation chemistry. This was published last year, and this is a really great example of new reactivity for what I'll call a classic reaction. I think, hydroformylation is a very established chemical processes, and sometimes people think there aren't gains to be made in this space. But there was a series of cationic cobalt catalysts with bidentate phosphine ligands, relatively simple phosphine ligands, in a lot of cases, that actually showed very high reactivity in hydroformylation chemistry. And this is just one example selected from the publication. Particularly when you look at the last row, the DEP-BZ ligand, so the catalyst on the left of the screen with the benzene ring in the backbone, you can get really good conversion at pressures that are typically lower than seen for cobalt catalyzed chemistry. What this really does is it opens the path to medium pressure hydroformylation chemistry. One of the areas that we like to play in Solvay is these new efforts for making exciting industrially relevant discoveries, right? The discovery phase is an important phase of catalysis, and I think this highlights that again, that this is really chemistry that can make a difference in established processes. Next slide, please. Sometimes you need, I would say, much more complex ligands or elegant solutions for different catalytic challenges. If you look at, say, the palladium catalyzed methoxycarbonylation of tetramethyl ethylene, which is shown here in this reaction scheme, for something like this, you need very bulky ligands. So in the ligand on the top here has these 4 tertiary butyl groups, and the one on the bottom has tertiary butyl combined with pyridyl groups. These can be built up from simple secondary or primary phosphines, but what they do is they really offer you some very low catalyst loadings in this type of reaction, to get your formation of your desired methoxycarbonylation product. These ligands as well offer a really important point that sometimes a ligand can offer you a variety of different reactivity, and you don't have to search for, say, 10 different catalysts for 10 different systems. These products are very robust as far as the diversity of the catalytic reactions they can do. There's a variety of different derivatives they can actually function on this reaction for. And they can actually do the conversion of bulk ethylene at very high turnover numbers, well over 1 million, and very high turnover frequencies at really good selectivity as well. And so these numbers are for that bottom ligand where you have the pyridyl and the tertiary butyl ligand here as well. Next slide. So the next reaction I wanted to mention is about hydrogenation. So hydrogenation is a really important reaction for converting alkenes and aromatics to saturated alkanes and cycloalkanes. A lot of this chemistry is done by heterogeneous catalysts that are very heat and energy intensive. There also can be non-selective in a lot of cases. Homogeneous catalysis is really nice because it offers the ability to do hydrogenation under milder conditions, but also in a chemoselective route. So if you look at a ligand like Chirophos, the Rhodophos CP100R, and the hydrogenation of this aldehyde here, you can do this over a ruthenium catalyst and get very high conversion to just the alcohol. So that's really important if you're just looking at converting to the alcohol but keeping that functionality of the olefin within this system. Homogeneous catalysis, and particularly ligand sets like Rhodophos CP100R, can offer nice solutions within that space. Next slide, please. Changing gears a little bit, I'm just going to mention about phase transfer catalysis in petrochemical industry, and particularly how it relates to the alkylation reaction. Alkylation to C8, we talked about this a bit earlier, is used in the production of gasoline. A lot of processes industrially require very harsh conditions, such as hydrofluoric acid and sulfuric acid. These are harmful for both the environment and people, and there's a lot of efforts to remove these from processes. If you take a phosphonium ionic liquid in the presence of a Lewis acid like aluminum trichloride, you can make these phosphonium species actually quite Lewis acidic, and they can actually facilitate the conversion of 2-butene to alkylate ultimately at near ambient conditions and in very good selectivity. And so they offer a potential alternative to HF or sulfuric acid for the alkylate process. Next slide. So also to touch on phase transfer catalysis, probably one of the most famous reactions that use this type of chemistry is the omega process to produce monoethylene glycol. So monoethylene glycol is a widely used product globally. It comes ultimately from the conversion of propylene oxide with CO2 to ethylene carbamate, and then this is subsequently reacted with water to get your monoethylene glycol product. In that first step, a phase transfer catalyst is critical, and products like tetrabutyl phosphonium bromide can be used in that step. This chemistry is really important from a sustainability and productivity performance. Compared to some of the more traditional methods of monoethylene glycol production, there's almost a 10% increase in the production. And there's also key advantages in this whole process that relate to energy. So things like less steam are required for something like this, and also less wastewater. And as I mentioned, using a phosphonium-based phase transfer catalyst can really drive a lot of this chemistry. Next slide. With that, I'll pass it back to you, Dino, to cover the last few points here.
Thanks very much, Eamon. And so this example of use of some phosphine oxides in the acetic acid process is one of my favorites. It's interesting because it gets us thinking a little bit outside of the box in terms of the typical phosphorus as a ligand in catalysis, but rather in this case, the phosphorus component is actually serving a different role. And so what's happening here in the carbonylation of methanol, which is a long-established route to acetic acid, we have rhodium catalysts that carbonylate methanol via addition of carbon monoxide. And in many cases, they use added hydroiodic acid or methyl iodide. What that means is this process is run in a very highly acidic medium that can quickly corrode reactors, process vessels, etc. And in this particular case, Cytop 503, which is on the left, it's a mixture of N-hexyl and N-octyl phosphine oxides, so a distribution of tri-N-hexyl, tri-N-octyl, and everything in between, those oxides of those phosphines. In this case, the Cytop 503 is used to reduce corrosion. So the chart, the table on the bottom left shows the impact on corrosion of slowly increasing the amount of Cytop 503 added to the process. So from the first entry having no 503 added, you see 0.5% loss in weight of a stainless steel coupon. When you add up to 1 molar Cytop 503, the loss in weight is substantially reduced. Which is, of course, important if you're operating large-scale assets. The nice thing here is that if you look at the table on the right, not only does the Cytop 503 reduce corrosion, but it actually improves the activity of the process. So if you compare those 3 entries on the right, you see that after 912 seconds, the amount of active rhodium is down to 6%, and the feed conversion is only 44%. When run in the same way, but adding triphenyl phosphine oxide, so that's the middle entry in the table, the time is certainly longer, so the lifetime of the metal is longer relative to no added phosphine oxide, but the conversion isn't significantly improved. Most sort of surprising is the addition of the Cytop 503 extends the reaction time substantially. After 1800 seconds, there's still 36% active rhodium left, and the feed conversion is exceeded 80%. So this is a really interesting example of the use of a phosphine or alkyl phosphine derivative, in this case a mixture of oxides, for something other than a ligand in a catalytic process. So it encourages us to think outside the box a little bit in terms of how we use phosphorus or how we view phosphorus in the field of catalysis. And so with that, we'll sort of start to wrap things up here. And that example is a great segue into, why work with Solvay. So with Solvay, certainly you get the speed, flexibility, and intimacy of a small company with strong corporate support. But you get the experience that comes with our history in phosphorus chemistry and our ability to think outside of the box and using that depth of knowledge to generate creative ideas. Beyond our ability to supply, our ability to scale, we have a proven track record for developing innovative technologies and practical routes to market. We have a very broad research organization, so we bring to bear the strengths of a large multinational organization like Solvay. We focus heavily on safe handling and processing of both lab and large-scale materials. Product stewardship is at the heart of everything we do, and we support the catalysis applications via a strong experience in logistics and registration and toxicology, etc. Solvay brings to the table everything needed to commercialize technologies, and of course we've seen some examples today of some very different technologies, very different chemistries. And because each company or each organization has its own feedstocks, its own equipment, its own objectives, really what the industry needs is someone who's able to supply custom technologies or custom solutions to suit the needs of each individual application. And like I said earlier, Solvay has many years of experience providing, in this case, specific ligand solutions. But leveraging our ability and willingness to partner with our customers or end users to develop and create sustainable, cost-effective, value-added solutions. And so really, we're always interested to hear about the next ligand challenge that the future holds. With that, I'll just finish up by thanking everyone for their participation, and particularly Ashley and Casey at Strem for organizing the website, the webinar, and also helping us to further our partnership in making this technology available to the broader research community. Thank you all. Ashley?
Thank you, Dino. Thank you, Eamon. That was a great presentation. So now we'll have time for some questions, but before we take questions, I do want to note there is a URL at the bottom left-hand corner. You will be able to access the video from today's webinar in the upcoming days, and you'll also be able to see the products mentioned during the webinar as well. So now we can go ahead and take some questions, and just a reminder, if you have any questions, please submit them in the question box in the GoToWebinar control panel. Also, if we do not get to your questions today during the meeting, we will email you directly. Okay, so let's take a look and see what questions we have first. All right, so to start, what is capacity like and ability to supply globally?
So maybe Eamon, I'll start and you can jump in if I miss something here. So in terms of capacity, really our capacity to supply phosphorus technologies is unparalleled globally. So we have the capacity and the ability to supply anything from research scale to pilot to multi-ton quantities around the world. This is something that Solvay is heavily differentiated against its competition. So really, there's no restrictions in terms of the scale that we can participate in.
Great. Okay, so next question. Do you have any experience testing the hydroformylation catalyst in CO hydrogenation of formaldehyde?
I'll take that one, Dino. So ultimately, at the end of the day, we focus mainly on the production of the materials. When we get to application testing, we have a couple different routes that we work through. Sometimes the application is tested directly with the customer. Sometimes it's with a, say, university facility if we're trying to generate some other data. Solvay does have some testing capabilities for a variety of different reactions internally. Hydroformylation is not one of them. So typically what we do is we use outside labs or partnerships to develop data in that area space when we want to develop data there.
Okay, great. So third question, are you able to expand on the framework of customer-specific projects?
I can take that one too, Dino. Yeah, so ultimately what we like to do in those places is we really like to engage, say, with the technical community and the commercial teams within a company. So really understand, say, what the challenges that they're facing, what that unmet need is, and then help them understand how we can work with them. So, in some cases, you'll have someone come to us that has a process developed and they need production of a ligand at the commercial scale. Sometimes it's very exploratory, and those are really exciting ones as well too, right? Like where we're saying, we have some framework that we want to look at. In those cases, we can supply, say, secondary phosphines, primary phosphines to a company. We can also work with them on helping them understand, the commercial aspects of a scale up for a ligand that might be developed. Sometimes people want to use their own process. Sometimes we have our own processes to develop and scale up a ligand. But we can really help in that, screening phase in particular in early research from a cost perspective. I'm always amazed at the amount of processes that are developed around the most expensive ligand solution, because that question wasn't asked earlier. As Dino mentioned, as it goes from research to pilot, we have pilot facilities. We have a few different production sites that we have different size units at, different capabilities at. We have small batch plants and then up to full scale manufacture. And so we can walk hand in hand in that journey with an end user or customer to really provide to the most effective solution that will offer wins for both parties.
Okay, great. Also, just before we go on to our next question, a couple of people are asking about the presentation and when that will be available. You will receive an email in the next couple of days with the video, but you can also access it at the following URL, strem.com/webinar13 in the next day or two. Okay, so we will move on to the next question. What is your position concerning the synthesis and the use of supported catalyst for homogeneous catalyst? What's your position concerning this?
So maybe I can comment there. I think, so certainly we didn't really have any examples of supported homogeneous catalysis in our presentation. That said, you know, anytime there are phosphorus building blocks incorporated into either a solid support or a catalyst that's been supported, that's an area where you know, we have some experience because of our experience with the phosphorus chemistry. We don't necessarily offer, say, a supported phosphorus ligand per se. However, to get to those materials, we absolutely have the technology and the know-how, and this would be a perfect example of how we could work with a partner to develop a process and ultimately a means to supply something like that to the market. So we're always open to new challenges, and something like supported phosphorus ligands or phosphorus-based catalysts are certainly an area that we would welcome.
Yeah, and to that point, you know, there's a lot of stuff we didn't talk about on today because there's a lot of stuff we can't talk about. We do a lot of work under secrecy agreements with companies to help them solve very specific challenges as well too. And so we have a lot of different chemistry in the toolbox. It's actually quite large. Then we just couldn't cover a lot of that information today as well.
Okay, thank you. Next question. Are your compounds suitable for use on flow chemistry systems for production?
Boy, maybe I'll take a stab at it here. So certainly, I don't see why, you know, some of the phosphorus derivatives that we talked about wouldn't be applicable to flow chemistry. Again, this is an area where we may not have covered specifically in the presentation today, but certainly phosphorus and some of the derivatives could be used in a flow type system. I don't know if Eamon, you have any other thoughts on the flow chemistry?
No, like I said, it's really on a case-by-case basis. A lot of that work. So there's a lot of there is nice work in the literature around that type of chemistry that uses phosphorus ligands, and our production facilities certainly offer products that can go into that space. So if there's specific ones that you'd like to talk about, we'd love to have that conversation with as a follow-up item.
Okay, perfect. Next question. How does Solvay handle regulatory requirements for these materials?
I can take that one. Do you know?
Sure.
So typically what we do when we're evaluating a new product or an existing product, say that we're looking at becoming a supplier of, we work with an internal regulatory team that we have. So Solvay has a very excellent team of partners in our company that really are experts in that field. So we look at the countries that we're producing it in, the countries that it has to go to, what the regulatory requirements are, you know, if there's toxicity testing that we need to do, say if it's for Europe for REACH registration. And we have a team that we work with globally on that. So we have people within our business unit, and we have people within our business units that help that. We can take on a lot of tasks around regulatory. As I said, it's from you know, doing everything to doing as much as the customer needs and support. And so we do our best to support our customers with that function.
Okay, perfect. Next question. For rhodophoss NiCad and nickel catalysts in general, can alternative ligands be used?
Eamon, do you want to take a stab at that one?
Yeah, I was going to say ultimately yes. So you know, the reality is some of these compounds, like the rhodophoss NiCad, you really have a lot of flexibility within those systems. Ultimately, you know, any phosphine you can think of, you can coordinate to nickel. The production of those is something that we're quite strong in. Ultimately, at the end of the day as well too, you know, we have some advantages in that space because we can reduce the phosphine ligands and really build up the system the way we want to, or the way the customer wants to.
Okay, great. Next question, what is packaging like for pyrophoric materials?
So I can take a stab at that one. So this speaks to our history and focus on product stewardship and safe handling. So we have extensive experience handling and supplying pyrophorics at all scales. And so whether it's 25 grams of a pyrophoric ligand, or hundreds of kilos of pyrophoric liquids, we have specialized packaging for all of those. The great news is that Strem is equally capable and knowledgeable in the handling of even smaller quantities. And so whether it's a few grams of a material supplied in a SurePack cylinder, or hundreds of kilos supplied in things that we call big blue or big gray cylinders, they're tailored specifically to be handled under conditions. And for things like production scale activities, the vessels that we supply in make direct connections to process lines to completely exclude oxygen or moisture. And so that, from the point of view of safety, is critical, but also speaks to quality and preservation of the high purity of the materials as well, avoiding oxidation, etc.
Great. So I think we have time maybe for one more question. So last question, there are effective ways to remove trace metals using scavengers. Can your phosphines be scavenged from reactions as well?
So in some cases, yes. So it really depends on what else is in that system, right? So there's things you can do like oxidation of a phosphine to remove it. There's stripping of phosphines. There's coordination complexes you can put in to react with them. So it really boils down to what options are available for a system, and how it's compatible or not compatible with what you're targeting.
Okay.
Yeah, that's the nice thing. Just to add to that, that's the nice thing about phosphorus, is that there are so many reaction pathways that a number of tools exist to treat or remove the phosphorus after process. Like Amy said, you have things like oxidation, but you also have options like quaternization, and then other reactions with things like sulfides and that sort of thing that have been used and well known in the literature as well for treating residual phosphorus components.
Yeah, and one comment too, I just wanted to quickly make, Ashley, so I know that was our last question here, is one question that didn't come up was around cost of some of the products. And I think one of the points that we want to make clear for everyone here is, specifically with things like nickel catalysts, is we have really strong economics around products like that. We have a lot of capacity with those type of products, and those larger volumes allow us to offer not just different solutions, but lower cost solutions into the market as well.
Great. Well, I think that's all we have time for. So thank you everybody for joining today's webinar, and we appreciate you being here, and we hope you join us for our next webinar. Thanks again. Have a great day.